Good.
All right, okay. So, first off, a bunch of logistics. I do not have everyone's idea for what they want to present as the final project. That looks okay. Looks okay? Yeah.
Oh, spirit.
So, if you haven't one, please let me know, and we'll make arrangements to get you spun up. So don't forget. Number two, how are projects doing? Good? Good. Yeah.
When you're finding all two faces in the beginning,
Yeah.
can you try to triple loop before
Finding all the two faces in the beginning, what way? Beginning of what?
like in the Viator's riffs?
Yes. Is it a triple loop? You could do it that way. Yeah. Yeah. So you could loop over all. So there's fundamentally two ways you could build Viator's riffs complex. The first way is you can start up and try to build out all the edges. So take all the pairs of points.
Right.
Fill out all the edges. And then do something that's like an induction step, which is once you have the K faces built out, you can build up the K plus 1 faces
Right, by checking if you
by checking if you've got all of the various subfaces. That's one way to do it. And that does involve a bunch of nested loops. The other way to do it is sort of bottom up. The top-down approach is you start out with the biggest possible simplices you can come up with.
Yeah.
So essentially say, take the simplex, the however many points you've got, simplex, put them all into one big honking simplex, and ask for all the faces of that, and check them, one by one. Are all the points in there pairwise distance within range? That also works. If you're smart about that, both of them involve walking over the same number of simplices, but the bottom up one, where you check to see if all the subfaces are present, that checking if a subface is present is not necessarily efficient because the ordering might be different. So that can be somewhat of a problem. Now, if you use the K sublists function that I gave you, then that preserves order. And that's a useful thing to keep in mind. But if you want to be assured that you're not screwing up the ordering, you can instead of comparing lists, because lists cannot be compared for equality in Python, you can do something like this. You could say, transmute your list into a set. So let's say 1, 2, 3. And if you want to know if this list here is equal to another list, you can't say, unfortunately you cannot do this. This does not work. Although you'd like to be able to do this. Although you'd like to do this, this is not defined. And sadly, because I would like it to be defined. But it's easy enough to write such a function where you use the following methods. Use the is subset method. This will give you a Boolean, and you can pass it another set. Is this a subset of? Oops. And the same thing, just the other way around. That works too. That's a good way to check set equality. Yeah.
So when you follow a set with a dot and then some words and then open parent, that is called an option?
It's called a method.
Called a method.
Well, when you what we've got a list. A list is not only is it a list of objects, but it is itself an object. It has a bunch of methods. What we're doing here is we're constructing a new object. An object that is a set object, is a set class, and that has a different set of methods, one of which is subset. There's also is member, and a whole bunch of other things. Yes, and this isn't the standard, this is actually standard Python, it's not NumPy. This is the base Python language.
So a method is kind of like a function.
It's a function that's tied to a particular object.
Right.
Yeah.
Very nice.
Do you have a question?
Yeah, so in the Viator's riffs function, you have like a max dim equals 3.
That's right.
So in the output, we should only have 3 elements.
4.
we should get 4.
Well,
So I mean, like, if it's max dim equals 3.
if it's max dim equals 3, the length of the longest list will be 4. Yes, remember, number of elements in the list is 1 more than the dimension. This is a 2-dimensional simplex. Okay? Other questions on this? Okay, all right, well then. How far are people at this point? Getting through Viator's rips? Getting some chain complexes built yet or not yet? I saw 2 chain complexes built, or attempting to be built anyway. Viator's rips. Okay, all right, that's where most people are. All right.
Why don't
fair
you
enough.
write, it's like a 2-line function to write your own set.
Oh yeah, that's fine. That's fine. In fact, furthermore, you could even subclass the set and then have your own method, an equality method. In which case, then you can use it in all the various searches and sorts and all that
Yeah,
good
but then
stuff.
I'd have to learn more about Python's object-oriented features.
Can you define your
I
own
missed
method?
that. What's that?
Is it possible, you can define a function, can you define a method?
Yes, so you can create your own objects, and
Yep.
in fact, you can create your own classes and define their methods.
That's right. And in fact, and furthermore, for reuse purposes, you can define what's called a subclass, which is here's a class like set. I'd like to make something that's got all the same methods as set, but I'm going to modify them a little bit.
And that's called inheritance.
And that's called inheritance, and that's a very handy thing as well.
If you think
So
it's
this is
neat,
why
take 2 to
Python
1.
is so nice.
Well, this is why object-oriented languages are nice. Python is one of them.
No.
And Python is very lenient about how you do this. Java also allows you to do this, but it's a bit more strict about how it's done. Okay.
Master of understatement, Dr. Roberts.
Master of understatement. Java is kind of a bureaucratic jerk, but that's more or less the way the language goes. Anyway, all right, well then. Okay, well with that in hand then, let's go back to where we were last time. And I begin with an admission of guilt that I got sidetracked, probably due to jet lag, for having the wrong number of generators as a goal. So let me try to rectify that problem. If you've watched the YouTube video, I don't know if you have, but I've actually annotated the YouTube video by writing all over the thing where I screwed up. So I actually comment on my board work, so you can see what's going on.
Turn on the video camera.
What's that? Yes, video is on. Yep, we're good. We're good to go. Okay, right. So, for persistent homology computation. And that's what we're in the midst of trying to do. And last time, we had we were computing the persistence of a very particular filtration. Filtration looked something like this. X0 is zeroth space was just 2 vertices. And X1 was those same 2 vertices. This being a filtration, I'm never allowed to delete simplices. I can only add them as I go. So I just added on that edge. So this is the persistent homology of this. So we're aiming for one is a subcomplex of the other. And what I argued that H0 of this filtration should have a very particular barcode diagram. And I said something of the sort. It should look kind of like this. This is time 0, this is time 1. These are our 2 components, and this is our 1 component here. We have 2 connected components here, we've only got 1. So I started out with 2 connected components. One of them ought to die, and the other one continues. They're both born at the 0th index, but only one of them persists until the 1 index. This is all fine. And I think I had labeled this one A and this one B, which again is also fine. So that's where we were. Now, the place where I screwed up was I looked at this and I said, well, these ought to be labeled somehow. And I said, well, maybe I should label this first one as being something like 1, and this one here being like 1 plus or minus t, where t is sort of keeping track of my persistence filtration. This is really t to the 0, 1 is t to the 1. If I had a 2 in my filtration, that would be t squared, etc. This too is fine. But I did something rather foolish. If I were to just look at the first filtration alone, what is the dimension of H0? If I forget about x1, what's the dimension of H0? Should be 2-dimensional. Why? Because if you look at the chain complex, what's the 0th chain space? It's 2-dimensional. What's the dimension of the first chain space? 0-dimensional. So the image of that is definitely 0. The kernel is everything, so the kernel is 2-dimensional, so it's 2-dimensional. Everyone catch that? Follow that reasoning? Okay. So my x0 should have been 2-dimensional. That means this part here should have been 2-dimensional. Now over here I only have one connected component. There's something going to be in the image of the boundary map, and that's going to wipe out one of the components. So this end should be 1-dimensional. The problem is, how can I have a 1-dimensional space as or rather a 2-dimensional space be a subspace of a 1-dimensional space? I just can't do that. I really need the 2-dimensional space the whole way through. Yeah.
So just because x0 is a subset of x1, that necessarily means that the homology...
No, not exactly. But my point is this. What's going to happen is this 2-dimensional thing is going to have to map into this 1-dimensional thing. It's not a subspace of, but it will map into.
Okay.
Remember, this inclusion is really a simplicial map. I can define where each of the vertices end up over here. If I tell you where vertex A goes, where does it go? It goes to A. Where does vertex B go? It goes to B. There's no other simplices to worry about, and so I'm done. That's a simplicial map. If you remember, simplicial maps induce maps on homology. So this will, in fact, take my homology here and map it as my homology here. But now what I want is I want an umbrella homology, something that holds all of this information for me. So it needs to be at least 2-dimensional in order to write it down. And so the problem is that what I wrote down next is wrong. I'll write it in red.
So where does that umbrella homology live?
Okay, so we got to build that, and I'll explain that. And in doing so, rectify this wrong. I said that H0, this persistent H0, maybe I'll put a P in front of it, is spanned by something that looks like 1 plus or minus t, plus then some kind of boundary 1. That's wrong, because really I need 2 separate generators here. Persistent H0 is equal to span. Remember, this is the span over RP. All nomials are my ring. 1, 0 plus image boundary 1, comma. That's a coset, and here's another coset 0 plus or minus t. And by which I mean I pick one or the other side. This is what I'm supposed to be doing. Okay. And then we went off in various kinds of exercises trying to make this sort of thing happen, and kind of came inconclusively to the end. And the reason why I came inconclusively is because it just wouldn't work. Okay. So, now given the right structure, let's make it actually work. And let's answer Dave's question about how this umbrella thing ought to work. So the point is, what we want to do is we want to define some chain complexes that are going to keep track of all of the various simplices, and they're going to work at the level of the biggest space over here. They're going to work at this level. They're going to work over there, and I'm going to label the simplices again with the birth time when they show up by labeling them with t to the birth time in some fashion. That's really the idea. Okay, so now let's make this happen. And I think maybe the right thing to do is to write down what the definition of the boundary map ought to be in this context. Because the boundary map, of course, drives the whole process. Okay. Point is, we want a chain complex. This chain complex will, however, consist of matrices whose entries are polynomials in T. And then we're going to do all our kernels and images and all that stuff on those polynomials. Basically souped up high school algebra. Doing linear algebra on regular old algebra, so to speak. Okay, so what I need to do is I need to define what that chain complex is, and I'll define it in terms of this example. I'll leave some of this up there so we can keep track of it. We only have one boundary matrix in question, and I need to define what the chain spaces are as well. Now, my point is, I'm going to build everything in terms of the final space, the biggest space. So all the simplices that show up in the biggest space are going to show up. So the principle is that all the simplices in the biggest space are present. So in particular, let me now actually define the persistent K chains. Persistent K is not really a space anymore, it is a module, because the coefficients come from a ring. So this is a module. In fact, it is something called a free module. I'll write that down and I'll kind of explain what that means. Over polynomials, ring RT, and it's generated by, or has a basis, if you will, okay, simplices of X.
So polynomial slash ing?
Ring, polynomial ring,
Ring, oh.
R-I-N-G.
Okay.
Polynomial ring, R of T. You should think of this as being, roughly speaking, the same thing as we did before, just in fancy language. Free module is vector space is a free module. All vector spaces are free modules, not all free modules are vector spaces. It's a strict generalization. And polynomial ring, well, that's basically like the field, so the real numbers, the coefficients. So this thing here, this is like a vector space. Not exactly a vector space, but it's like that. These are the coefficients. And generated by, that means I'm specifying a basis. But again, we don't use the word basis because we're doing a vector space. But this is exactly the same definition that we had before, just dressed up a bit. So in particular, these guys are going to be labeling the rows and columns of our boundary matrices. So in essence, rows, columns of boundary matrices are labeled with simplices of X. And X is the last guy in the filtration, the biggest one. Okay. Just as before, none of this is different. The formalism feels a little bit different, but it's just the same. Okay, so now what I want to do is I want to specify the boundary matrix. The boundary matrix is going to have the same sparsity pattern, the same zeros in the same spots, as would the chain complex for X. But rather than having plus or minus ones, I might have some t to the k's, plus or minus. Plus or minus t to the k's. So, boundary K will go from PCK to PCK minus 1. As before, it's a matrix. It's linear over RT now, so it's linear over multiplying through by polynomials. So my polynomials are my coefficients. Fine. So it's still in matrix form. And here's how this goes. That I need to keep track of when the birth and death times of each, or rather, no death times, the birth times of each of these simplices show up. And what the boundary matrix is going to do is, look, I haven't put it in here. I haven't put the filtration in here, so it's got to show up here. Are encoded. Or rather, of the entries, matrix entries, and the important thing to realize is that it's not the absolute birth times that get encoded here. It's the relative birth times. So it's telling you about the difference between these things. The difference in the birth times is basically what gets encoded. Okay, so here's the idea. It's a matrix, right? It's a matrix. It's something that I can put in parentheses around it. Perhaps the most general definition of a matrix is a thing in parentheses. All right. Now, things in parentheses that have rows and columns, in fact.
No.
That's awesome. All right, so, has rows and columns, and those rows and columns come about from there being various, in this case now I'm going to be more specific, simplices. So I have a simplex here, and I have a simplex here. And I need to know, what am I going to put in this spot? Okay, well, let's see here. I need a simplex. Let's say that I've got a k simplex here. V0 up to Vk. And here I've got a simplex V0 up to Vi. I'm going to leave that out, up to Vk. So as before, I'm going to take my sign from the deleted entry, minus 1 to the I, just as before. This is exactly the same formula we had in the past, but now it's in a matrix form. But now, I'm going to label these. I haven't put the birth times in. This is thus far just the simplicial chain complex for X. Now I'm going to put in the birth time information. And the way I'm going to do that is I'm going to tell you that the birth time is B. Here the birth time is capital B. Now, what can you tell me about the relationship between the birth time little b and the birth time big B? The birth time of a simplex versus the birth time of its faces.
Simplex has to be after.
Simplex has to be after the faces, or at least certainly no earlier, because I need a simplicial complex at each time. Simplicial complexes always have all of their faces. So in particular, the birth time of this guy has to be greater than or equal to the birth time here. Okay? So what we do is we put in here that coefficient I'm going to put, rather the exponent I'm going to put on the t, it is non-negative because of that observation. So the observation is that this is non-negative since x c, need another guy, is always an abstract simplicial complex. The simplex, if the simplex is there in the birth time, all of its faces has to be no earlier, or rather no later. Okay. So in the way good mnemonic for this is you take the birth time here, you've got the birth time here, and what you do is moving from here to here, how much time do I have to add? What's the gap in time? That's what this t is. This t is the gap in time. Telling you how long this simplex was around, or rather this face was around before a simplex containing it decided to show up. Okay. Now, interestingly enough, this thing forms a chain complex. It's proved in the paper that we mentioned. And so it's useful to take a look at this thing then, and to see what it does now in our example. Now, fortunately, the matrices are not big, but they are now containing polynomials. I mean, they're really not big. Okay, here we go. Okay. So what boundary matrices do I have? I don't really have boundary 0, which is a zero matrix, and boundary 1 in this case. What's boundary 1? Well, I'm going to label the rows with A and B, the 0 simplices. I'm going to label the column with A, B. Well, as before, I can easily supply the signs. And what should I put in as the rest of the expression in those entries? T to the 1. What goes here? What goes there? What goes there?
When A and B show up, is that what we do?
Yeah, so what's the difference in the birth times of those two things? Those two simplices?
Oh, A and A, B?
Yep.
There's no difference. They're born at the same time.
A and B are born at the same time, but compared to AB.
1.
Before.
Yeah,
Right.
before, and how much before? 1. Alright, so that's the boundary matrix then, according to this formulation. Now, let's see if this comes up with a space that looks much like the one that I drew. The barcode that I drew. Alright, so let's see what happens. So, what is H0, or rather PH0, is going to be the kernel of boundary 0 modulo the image of boundary 1. Well, the kernel of boundary 0 is everything, right? Don't think of it necessarily as a two-dimensional image, as a two-dimensional space. Because what's the dimension of this, the image of this space? What is the dimension of the image of boundary 1, if I were to think of it as a vector space? 1. And this is a two-dimensional thing. If I had a vector space, this was a vector space and this is a vector space, then I would be left with a one-dimensional quotient. Not so here. I don't have a one-dimensional quotient. The module that is generated in this way, generated as cosets in this way, is not one-dimensional. It's still two-dimensional. So let's see what that looks like. And those two dimensions are in fact the bars. So let's see that. And be very explicit about it by doing what we're doing at the very end of the last class, where we're starting to cast about a bit. But it's actually the right thing to do here is to write down the polynomials and actually see what happens. Because what happens when you multiply by t? What does it do to a polynomial?
Raises the degree by
Raises the degree by 1. Okay, wait. If I had, are there any polynomials that cannot be found by multiplying something?
constant.
Yeah, the constant polynomials. They stick around.
This was on our algebra homework last week.
That was on your algebra homework. Excellent. So that's actually kind of the reason why this quotient is not going to turn out to be one-dimensional. Or rather, the terminology in module theory is rank 1. All right. So now let's examine it. So
They really stole terminology from linear algebra, didn't they?
you know, okay, is what it is. All right. So let's write down the kernel of boundary 0. That's the span over RT of 1 and 1, 0. This is B for all practical purposes. This is A for all practical purposes. Really, this is, this guy here is B, this guy here is A. One, in black I've written out in coordinates, vector components, the other one just abstract. All right, now as far as the image is concerned, that is literally the span. I'm going to be a little pedantic here and write it out as such. That's literally by definition what it is. Now let me write it out in terms of polynomials. Let me take a polynomial P. It's the set of all pairs of polynomials minus P of T plus P of T, where P of T is a polynomial. Okay. So similarly, now writing it out not as a span, it's RT, Q of T, such that RT and Q of T are polynomials in T. Okay, again, just write from the definitions. Wait, I messed up order. T P of T, T P of T. Of course, I didn't multiply it by the matrix, so that's going to be wrong. All right. So in particular, none of these polynomials here are constants. Key point is no constant polynomials. Okay. So now I'm going to look at a particular coset. My coset is I'm going to take the kernel guy and I'm going to add on all the possible images. take one kernel representative, add on all the possible images. All right. So, set of all kernel guys, RT, QT, plus now I'm going to take the set of all of these things. Minus P of T, minus TP of T, plus TP of T. RT, where R and Q are as such. And watch those curly braces. Okay. So of course I can do a little bit of rewriting here.
Is it P star in R and T?
No,
Of T.
those are of T's. It's supposed to be a P of T.
No.
Got cramped, sorry. All right. So think of them really as R of T minus TP of T, Q of T, plus T, P of T. Where here's the P is quantified over inside, and then the R and Q are quantified on the outside. Okay. Now, by choosing particular P's here, I can force these vectors into a particular form. In fact, without really straining too hard, I could arrange that the top guy turn out to be spanned by just the number 1 plus a bunch of T times P of T, different P of T. So notice one representative in each, or in each coset as the form. Something, there's a star. In actual fact, put a 1 there. Just by choosing. By choosing what? By choosing, in fact, actually, let me make it a, yeah, that's fine. By choosing R of T minus T, P of T equals 1. Of course, I can solve that particular equation without any particular stress. Why? Why can I always want to find this given this? Well, R of T is a polynomial. It's not always going to be 1 per se. It's going to be some number. This is some number, not necessarily 1. I'll call it A.
Because polynomials are vectors.
Yeah, well, even more so. I might not be able to make it equal to 1, but I certainly can make it equal to A. Why? Because I can basically make the P of T be all the coefficients of R of T that I'd like to get rid of. Hit it with T, now it's up 1 degree, and I wash out all of the stuff up here. So this R of T looks like R0 plus R1T plus R2T plus etc. I want to get rid of T, P0 plus P1T plus etc. I can wipe out everything but R0 by choosing the P's appropriately. This will be an R0. By choosing those P's appropriately.
Wait, hang on, but don't we want this to be a constant, we want the difference to be a
We
constant.
want the difference to be constant, so we can do that. That's not hard.
But the constant has to be R0.
0. I mean, in the end, we will span it by, it'll be spanned by something with a 1 in there. Fair enough. That's not so bad. Okay, so we can end up making that happen. Now, what other representatives are there? Well, I can kind of do the same thing on the other side, but what happens if I do this, if I make this particular choice? Well, I probably won't wipe out a constant in the Q side. I'll wipe out a lot of stuff in the Q, but not necessarily everything.
Do we have that R of t and E of t need to be of the same degree?
No. In fact, there won't be usually. P will be at 1 degree lower than R, because I'm going to bump its degree up.
Right.
Okay. So what I'm trying to do is I'm trying to, I mean, this is the answer in some sense, but it's kind of opaque. We started out with something that was generated by something of degree of rank 2. That's what the kernel was. And we're quotiening by something of rank 1. It's definitely a subset, definitely even a subspace in the right way, or submodule. But the question is, what does this quotient look like? So that's what we're trying to do. We're trying to figure out what quotient is. In exactly the same kind of way we would have had to do, and in fact, exactly the same way we did do at the beginning of the course with vector spaces, by looking at the cosets. But now things are a little bit more subtle because we've got these degrees floating around, kind of causing some problems. Okay, so thus far, if we do this, if we choose those particular, take a look at that particular representative in our coset. So, this representative, looks like the following. It looks like A, and then we've got Q of t plus T, or let's see here, plus T, P of t. Now, P of t has been nailed down for us. This is now determined by the fact that we're trying to wipe out all those coefficients in R. But how many degrees of freedom remain? If this were a vector space, how many degrees of freedom would remain?
Degree QT minus 1.
Well, what do I mean by degrees of freedom?
How many coefficients can we freely choose?
Yes, and what are the coefficients?
They're an R of t, so therefore we have
They're
one.
polynomials, right? Right, they're polynomials. This thing down here is still, for all practical purposes, an arbitrary polynomial. This thing here is an arbitrary polynomial. So every time we lock down one of these degrees of freedom by choosing our P in the right way, we're still left with another degree of freedom. That means I've used 2 degrees of freedom here. There were 2 degrees of freedom still present in this thing. This is still an arbitrary polynomial. So over T, 1 degree of freedom still remains. So we've done our quotienting process. I've used up, by doing this here, I've tried to use up a degree of freedom. So that would be like I've used up 1 dimension of my vector space, but I still got 1 left. To constrain, our t. So pH has 2 degrees of freedom. Still. Okay, so this thing's running 2. So now what we want to do is we want to understand what it looks like. Okay. Well, that's sort of interesting. So what we've done is we now know that every coset has a representative like this. Now, what that means is now this means we've got the following basis. Now let me write this out then. Let me take my representative and write it out in a useful-ish way. H0 is the span over RT of that sort of thing. A 0. Oh, wait, why am I saying span? I'm not supposed to be saying span. Of a 0 plus zero QT T. And then there's still this image floating around, but we've broken up the thing that was in the front. How do I want to write that? That's not quite right, is it?
Comma?
Yeah, kind of like comma. Kind of like comma. The problem is I'm being algebraically inept here at the moment. Because I just erased part. Let me write what I had before. All right, let's pull from notes. What did I have here before? I had, at this stage, this was an R of t, this was a Q of t, this was a minus t p of t, and this is a plus t p of t. Okay. And this is my inner coset over p, and my outer coset is R and Q. Okay, all right. All right, so now I want to use the insight that I had. Right. So the insight that I had was that I was able to find a particular representative of this coset was by choosing P appropriately. By choosing P appropriately, I can rewrite this guy here in that form. Right. Okay, so by doing that, choosing P appropriately, so different P now, Q of t plus t, P prime of t. It's a different P. Here. Now parameterized over P prime. R and Q.
Didn't you choose this such that we didn't need that second half? Because it would be A0, Q.
Well, remember, I've got the whole coset. Got the whole coset. So what I've done is I've just grabbed an entry out of my coset to knock out the polynomial, the degree 1 and higher stuff. But I still have the rest of the coset floating around. Remember, I'm working.
Okay.
All I've done really is I've said I want to pull out one of the entries of this coset to wipe out this coefficient, but I still got the rest of the coset there.
Okay.
So there's the rest of the coset. Okay. So I've just rewritten this. Now let me pop this apart. In the way that I was trying to do up there, I got it messed up. All right, so now this is A 0 plus 0 Q of t plus t, and this is, right, this is not t p prime. This is now the actual particular one I happen to choose. But it happens to be arbitrary. Okay, plus, than the rest of the coset, which is in terms of P prime. And just to drive this point home, what I've chosen here, this P has been chosen very particularly. The non-constant part of R. So now P is fixed. P prime is still the rest of the coset. Okay. So what I've done is I split it up into two different pieces. Without loss of generality, I can add another one of these guys here, parameterize over it. This is going to get very long. So it is. I'll call this one P double prime T. These are supposed to have T's in them, right? Yes. Right, and now I'm parameterizing over P double prime, plus another set, another coset, which has got the other stuff. Say triple prime. I don't know. Eventually I'm going to run out of prime space here, but go with it.
Use tildes.
Start using tildes, exactly. And all of these things are quantified over R and Q. Okay, there we are. Okay. Did everyone follow what I did to get through this? Okay.
I followed up until.
Yes?
Yeah.
Yes? Everyone good with this? Everyone good with this?
Why are we still needing to define R in the second?
R and Q, because I'm looking at the entire set of values in this quotient. So I've not switched to spans yet. So I'm parameterized. So R and Q will, A was essentially the leading coefficient of, or the monic constant part of R.
So then
And here's Q.
where do we define our polynomial P of T then? Would that be inside?
Right here, we've built it up.
Okay, so it's no longer, it's just, yeah,
It's-
never mind, never mind, yeah.
It's locked down.
Yeah, never mind.
So, okay, is everyone good with this? Yeah.
So the P cancels out part of R,
That's non-constant. Yeah.
but P and R are, oh, I see. P and R are being added in the above.
That's right.
Okay.
They're being added in both, exactly. Yeah. So we're good with this one. Good with this one. All I've done here is I've just split this vector into the sum of these two guys. Now, when I go from here to here, what I've done is I said, well, as far as sets are concerned, remember the P primes are arbitrary, so I can split them up into the sum of P double prime and P triple prime. And then just group them with the first or with the second. And that's what I've done, is I've grouped them with the first and the second. So I've got two cosets, and these cosets are then formed as the sum of all the entries of these, which is exactly what's written there. Yeah.
Why did you choose to switch the negative from the
Top to the
top to
bottom?
the bottom?
Because I'm not paying as close attention as I should. It doesn't really matter because the P's and P primes are arbitrary anyway,
Right.
but you're right, for the sake of clarity, yes, thank you. Okay. Everyone with me thus far? You with me? Where did others do?
I'll watch it.
You will watch the video, all right. Okay. Here's sort of the point now. What is this? This is a very particular space now. This is a very particular quotient. It's a rank 1 quotient space because this is parameterized by, just multiplied by one thing. And so This is now two separate generators. Now this is getting to the point of where we wanted to go with this. So now what I want to do is I want to think of these now not in terms of the sets, but rather in terms of what they're spans of. So my next equation here is going to write this guy as a span and this guy as a span. This is the linear combination of two spaces, or two modules. I'm going to form the sum of two modules. The first one is the span over our T of A0 plus all this junk here. So this is a quotient still. But up to isomorphism, it's the span of just this. No longer an equation exactly, because I'm now realizing that this is really being parameterized by just one thing. Remember, my coefficients are polynomials. Yeah. But I'm not done. I'm not done right. That's the first part. The second part is what? Well, it's 0, something else. Notice the first one I can say is definitely times a constant. The second one is not times a constant. It's times QT plus this particular, very particular vector. So this P of T vector now has been chosen to depend very much on A. So this is really very much a whole bunch of possible products of something that looks like a 1 times whatever this P of T thing is. Or not even, there's some division involved here. But basically it's something, some constant. B plus T, P of T. Something of the sort like that. Now when I go ahead and multiply this guy out, it looks very much like that. Did I do that right? No, I didn't. No, I'm not quite right there. Still wrong.
Shouldn't it be like B, P?
Yeah, I gotta do some factoring, right?
Yeah.
I gotta factor out my, yeah, right, it should be 1 plus T, P over Q or something like that, right?
Yeah.
Yeah, something like that. In any event, whatever this thing is, whether it looks like that or not, it's kind of a different character as this guy. These are different, and these are then, this is the bar starting at A, and this is the bar starting at B. And notice it's sort of definitely, whatever it is, it's got this T part. Yeah.
Why is it that in the first summand, we're allowed to multiply the A by a polynomial?
Oh, we are in the second one as well.
Yeah, but if we go down here,
Yep.
it's
Specific.
it's specific about the first summand is the vector A0,
Yes.
not the vector A0 times the polynomial.
Ah. Very good observation. Maybe I'm messing this up then. Oh, you're absolutely right, aren't you? Yeah, you're absolutely right, actually. Actually, that is the point I'm missing, aren't I? Okay, all right. Look, this is algebra. Gosh, all right. You're absolutely right. Right. What is this first summand then? What is it parameterized by? Now, you're right. Thank you, Dave. You've saved me.
The first summand is parameterized by A,
Which is a single real number.
Yeah.
Single real number. Single real. This one here is now, right, okay, there we go. Now we're in good shape. What is this one? This one is now 0, and this bottom thing can be anything. Span over RT. There we go. Okay, that works better. This is really then that first bar. This is, and has no t's involved. This second one here multiplied by anything is then, in fact, the way this thing looks like. Because it keeps going on like that. This is the second.
RT is required to be non-constant.
Well, it doesn't have to be, no. See, this Q is arbitrary. So I have an arbitrary polynomial plus t times some fixed polynomial.
Okay, but the polynomial could be.
But the resulting polynomial is anything. Right, there's that. This is an arbitrary q0 plus t times q1 plus t squared times q2 plus that. Plus then, this is arbitrary. And then this one here, though, t p0 plus t squared p1 plus, this is fixed.
But it's not against the rules for p to be 0.
Yeah, it's not against the rules for p to be 0, in which case then I still get an arbitrary polynomial.
Right.
Well, regardless of what p is, it's fixed, but it doesn't matter. This will still be an arbitrary polynomial. Right. Okay. So that first bar then doesn't last, the second bar does, and that's the interpretation of this homology. Now, that was kind of long and drawn out, and that was for 2 points in a line segment. This is why persistent homology is somewhat of a pain, and this is even the optimized way to compute this, is to do this all with the algebra. You could imagine doing this with a lot more, and this is where computer algebra systems really come into the fore. And the other observation now let me step back and make some optimality constraints, or some optimality discussion. Last few minutes. Thus far in this class, I have not been concerned about optimization. In fact, I'm following the computer science principle, premature optimization is the root of all evil. Which is to say, if I have code and I want to make it run correctness first, then make it faster. Unless you really have no other option. Like it doesn't fit in memory. Which also could be a problem. Keeping track of all of this stuff certainly consumes a lot of memory. One thing you can do that helps, and it's clear that it helps,
Get more memory?
to save on, buy more memory, yes. Buy more memory, sure. Now, if you don't have an infinite budget, that only takes you so far. Problem, doing linear algebra scales badly. Polynomial, but polynomial in the number of simplices. Ouch. Not so good. It's cubic in the number of simplices. I don't care who you are, but if you've got a 26-dimensional simplex, 26 factorial cubed is a big number, regardless of how much money you have to buy yourself a better computer.
I mean, that said, since you're using a 64-bit address space, there's still a finite cap on the amount of RAM that you can have.
Yes,
So,
that's bad too.
so that's your
And
constraint.
even if you have one of these fancier machines that has access to more memory, they do have such machines, still doesn't scale in your favor. So one thing to do that helps is to make the following examination of the matrix. When you look at your boundary matrices, it will never be the case that you have a column of all zeros or all ones. It will never be the case of that, because what would that mean? That would mean that you have some simplex that doesn't have any faces, or a simplex that's not included in any other simplex. I guess that could happen. You might have a row of all zeros. So you can certainly ditch all the rows of all zeros. What you can do is you can start trying to reduce. Start trying to row reduce. When you do that, you'll end up in this sort of situation. Stuff, zeros, 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 not zeros. It'll be kind of in this form here, or actually this is more stuff. It'll look like this. when you're partially done row reducing, because you've cleared a bunch of the columns. Or if you're column reducing equivalently, just transpose the thing. When you do that, here's an observation. Right away, you can see if you end up with any pivot columns. Any columns where you have a number and then another number on the same level before dropping down to the next level. Right when we were finding the rank, like we've done in the past. If this is something you care about, if you just care about dimension of things, what can you do? Well, I know right away that one or the other of these columns is going to end up being linearly dependent with the other one. These two columns are now linearly dependent. I only need one. The moment you see that, I've only partially row reduced this thing. The moment you see that, get rid of that whole column. Roll it out. Now, additionally, what else can you remove? You can remove a whole row from the matrix that you're going to multiply this thing by in a chain complex. So you get rid of this column, its corresponding row. And so as you're in the process of doing your row reductions, you can start blowing away all of these various columns and corresponding rows. And that will greatly reduce the size of your chain complex. It is, however, a greedy algorithm. If I started here versus if I shuffle the rows and start somewhere else, I get different rows being removed and different columns being removed. Yeah?
So the result you're claiming is that if you delete that column and the row from which that you're going to multiply by, that will change the homology?
That will not change the homology. And it's actually quite clear why.
Will it change the image in the kernel separately?
It will change what it will do is it will collapse something that's already in it. What it does is when you remove it, you keep track of it. You pull it out of consideration, but you now know this is in the kernel. So you keep track of it. So basically what you're doing is as you're deleting these guys, now you're keeping track of those. Now this insight in the paper we've been discussing out for the past two classes, this is actually the sort of final comment on that. The realization is actually you don't need to keep track of the whole matrix if it's a simplicial complex. Why? Because you know every time I have a simplex, it's got all its faces. And I know exactly what they are. And those are going to fill out the rest of this matrix. The only thing I need to keep track of in this boundary matrix now are all the differences, the birth and death times of the simplices. But I don't need to keep the whole matrix. I just need to keep the non-zero entries, of which there are very few of them. So I can keep a sparse representation. And then when I do my row and column reduction, most of the time I'm just removing pivot columns. So I end up saving a lot on memory. I don't keep track of all of the entries here. I don't keep track of all of this junk here. I just work with these pivot columns, and that greatly reduces both my memory and my runtime. And that's what they advocate in this paper. And in fact, that single algorithm is what made persistent homology actually something you can compute in a reasonable time.
Reasonable time being?
Reasonable time being that you could actually run it at all on a reasonable complex. All right, so you can actually do that. Now, subsequent to that paper is, I think 2005 is what I said it was. So that's 11 years ago. Not very long ago. Subsequent to that time, now 2008, 9, I think finally published in 2010, was a number of results that take it a little further and actually say, well, there's not just, this is an algebraic thing. There's a topological reason for when you can find pivots. And just by looking at the complex, the simplicial complex, you can identify when you should be able to collapse something. And really they look like this. Just draw a picture. My complex is off here, and I have a filled-in part here. This filled-in part here, it's a little flare. It sticks out the side of the rest of my complex. It's a little ear that sticks out of the complex. You just get rid of those outright. They don't change the topology at all. Because in fact, you can build a chain homotopy that collapses them. Just pulling this, build a simplicial map that takes this vertex to either of these two vertices. That induces a chain homotopy and the whole thing goes in the wash.
So where's the ear?
This thing here is sort of the ear sticking out of your, there's the other ear. So the point is the ears can just be collapsed in. Doing that sort of thing is much, much faster. And there's even a good way to find it, and that uses something called Morse theory, which is way beyond the scope of what we want to talk about. At least in the class right now. All right, and with that, that is all we had. Can you grab the, push the button?
I don't actually know how.
Just push the silver button at the top.